talk of the morning. Chao will talk about robust estimation and GANs.
Okay, thank you, Andreas, for the introduction, and thank the organizers for the kind invitation. Today I'll talk about robust estimation and its very interesting relation to this generative adversarial nets. So I will spend the first half of the talk to talk about how you can use various depth functions to achieve optimal rate of convergence for many estimation tasks in the Huber's epsilon contamination model. And then I will talk about how you can actually optimize something that is very similar to depth function using the technique of GANs. So the talk will be focused on Huber's model, where the data are generated from a mixture distribution. So for each observation with 1 minus epsilon, probability it is drawn from the true model that you assume for the data. And then another epsilon probability it is drawn from an arbitrary distribution, but you do not know what it is. So theta is the parameter that we are interested in estimating. You can think of it as a low-dimensional parameter, or it can be as general as a non-parametric function, or even the density function itself, depending on the setting. And I will call epsilon the contamination proportion and Q the contamination distribution. So let's start by talking about perhaps the simplest model where you need to estimate a multivariate normal mean in this situation. So how can you do that? Well, one of the most obvious estimator is you can just take the coordinate-wise median, which is defined to be the univariate median taken on each coordinate. A second choice is Tukey's median. It is defined in a slightly more complicated way. Basically, you seek to find the univariate median on each direction of U, and then sort of using this formula to combine all the univariate medians in terms of all directions. So which estimator is better? If you are familiar with those old literatures in 1960s or to 80s, especially those papers in Annals of Statistics, then one of the most popular notions to assess the robustness of estimators is called breakdown point. It is defined to be the smallest proportion of the data that you need to perturb or change so that you can change the corresponding estimator to an arbitrary value. So as an extreme example, for sample average, the breakdown point is just 1 over n, which means that you only need to change one of the observations so that you can entirely change the value of the estimator. So that means sample average is not robust. Okay, so for coordinate-wise median and Tukey's median, people have calculated the breakdown points of the problem. One is 1 over 2, the other is 1 over 3. That means you need to change at least half the data to completely change the value of the coordinate median. But for Tukey's median, you only need to do so for a third of the data. So from this comparison, you may think, well, coordinate-wise median is more robust, but this is not the complete story yet. Well, in addition to the breakdown point that assesses the robustness property, we can also look at the convergence rates. And in particular, if there is no contamination, then the convergence rates of the two estimators are the same. P over n, you cannot distinguish them. However, when there is contamination and you try to calculate the rates of convergence in the Huber's epsilon contamination model, then you can really see the difference between the rate of convergence, especially the second term that depends on epsilon. The rate for Tukey's median is dimension independent, while here you have p times epsilon squared. And this rate, it can be proved to be the minimax optimal rate in the Huber's epsilon contamination model. So this table tells us that, by this very simple example, tells us that Huber's model is the right framework to study robust procedure. Because if you do that in the Huber's model, you have to study the statistical property and the robustness property simultaneously, right? If you do these two things separately, but then you will get a misleading conclusion. You may think, well, coordinate-wise median is actually better, but it is not. Okay, so let me briefly talk about the intuition behind the definition of Tukey's median. So the idea of John Tukey is that if you can solve a one-dimensional robust estimation problem, then you can simply project your data onto or the univariate direction, and then sort of combine the univariate median into a multivariate median estimator. So let's consider a particular direction parameterized by a unit vector u, and then just project the data onto that direction. You calculate the proportion of the data on the right-hand side of this number and on the left-hand side of this estimate of this number. Try to balance these two numbers. So each one is approximately 1/2, which means for a candidate vector eta, its projection on this particular direction is close to the sample median of that particular direction, right? So this particular measure is sort of measures the outlierness of this number on that particular direction. So if you take minimum over all direction, this gives you an overall outline measure of the candidate vector eta. So Tukey's idea is just to maximize this objective function, which is called the deepest point, and it's defined as Tukey's median. Okay, and due to symmetry, you can actually rewrite the objective function in a simplified way. All right, so that's for the location estimation problem. Now let's try to talk about regression. For regression, let's talk about this simple Gaussian linear model where the conditional distribution of y given x is specified by this Gaussian linear model. And then is it possible to robustly estimate the regression vector beta using ideas similar to Tukey? Well, there is something called regression depth, and I'm going to introduce its definition. But the first problem, you notice that the observation you have is y, which itself is a scalar, so you do not really have a direction to project to, right? You only have two directions because it's one-dimensional, either project to -1 or 1. This is not enough for us to capture the complexity of beta, which itself lives in a p-dimensional space. So the first step you can do is to embed the response variable into a p-dimensional space by taking product between the covariates and y, and then you will have a p-dimensional regression problem. Now you can use Tukey's idea to project it back onto a one-dimensional subspace and write down the similar formula as Tukey's median. So this gives you the definition, what is known as the regression depth function. The maximizer of the regression depth is a robust regression coefficient estimator. And this is proposed by Rousseau and Hubert in 1999. Okay, so you may think, well, this is a more general idea than Tukey's median. Maybe Tukey's median is a special case of regression depth, but it is not true. Tukey's median is not a special case of regression depth. These are different concepts. So in order to understand these two depth functions, from a unified framework, we need to introduce something even more general called multitask regression depth. So here we actually generalize the regression model by considering a multitask regression setting where not only the covariate is multivariate, but the response is also a multivariate vector living in an m-dimensional space. So this is like you have m independent regression problem that you try to solve together. Okay? And the goal is to learn the regression coefficients that can be organized into a p by m dimensional matrix. Right? So the regression depth for this problem, it can be defined in the following way. So let's consider a matrix U that is of the same size of B that lives in P by M dimension. And then this U transpose X will be a M-dimensional vector. Y minus B transpose X is just the residual that you can calculate by fitting the linear model using this matrix B. And then the population version of this multitask regression depth function is defined to be the infimum over U over the probability of the inner product between this U transpose X and the residual is greater than or equal to 0. And then if you replace this probability by empirical measure, then you get the empirical version of the depth function. Right, so this is a more general version of depth compared with Tukey's depth and regression depth. And itself is a special case of something even more general called tangent depth that is proposed by Maziran in a 2002 Annals of Statistics paper. Okay, so some special cases we can discuss. The first case is when p equals 1, meaning that you have m response but only one covariate. And let's further assume that x, the covariate, is 1, then this just gives you the Tukey steps. Okay? And the second special case is when m is 1. So that means you only have, it's just a univariate regression problem with multivariate covariates. So that reduces to the regression depth function. So you can see that the multitask regression depth function is really an extension of both Tukey depths and regression depths from different directions. Okay, so to understand why it helps you to estimate things robustly in a minimax way, let's talk about two important properties of regression depths. The first property is that the deviation, yes?
Could you also get an inverse regression version of the depth? And, when you think of x given y? Like the supervised dimension reduction perspective?
I think you can, because the definition doesn't really depend on the data generating process. It's only when you estimate the behavior of the estimator the DGP matters. Okay, so the first property tells you the deviation between the population regression depths and the empirical regression depths. It's deviated by, the difference can be bounded by square root of p times n divided by n. Here n is a sample size and p times n is just the number of parameters in the model. So this is a simple VC dimension calculation. And the second property is the stability property of the multitask regression depths. It says that if you have an epsilon contamination, and then the regression depths can only be changed by the value of at most epsilon. So combining these two properties, you can actually prove that it actually achieves the minimax rate if you have a data generating process like this. For example, we consider an ordinary multitask regression problem where you have a random design, which is assumed to be Gaussian, and then given x, y follows a Gaussian linear model. Let's assume the pair of the data are ID generated from the Huber's epsilon contamination model, and then the maximizer of the regression depth function can be proved to achieve these two rates with respect to the prediction loss and the estimation loss. So for the estimation loss, you will have an extra kappa square, which is actually the smallest eigenvalue of the design matrix that is kind of necessary. And both rates are the exact minimax rates of the problem and cannot be further improved. Okay, so that's for the regression problem. Now let me move to the covariance matrix problem. So it's basically the same thing that you try to estimate something in the epsilon contamination model, but this time is a p by p covariance matrix that you're trying to estimate. So what can you do? So this is how we can generalize Tukey's idea to this covariance matrix setting. So I would like to illustrate the idea by this picture. So suppose we have this two-dimensional plot of the data points on a 2D surface. So again, I'm trying to project my data onto a one-dimensional direction. So let's look at this direction. And on this particular direction, you can actually, it's not too hard. It's not hard to figure out the scale of the data. Okay, so for example, like this, you can do that by calculating the median absolute deviation, which is a robust scale estimator. And suppose you can calculate the median absolute deviation on a second direction and then on the third direction and so on every direction. And then sooner or later, you can realize, well, the data cloud can be summarized into a shape of ellipsoid, which then corresponds to a covariance matrix estimator. So the idea is how to combine these median absolute deviation from each direction. Well, if you write down the formula, it looks like this. So you first project the data onto the direction of u, and then take square, compare it to u transpose gamma u, because on that particular direction, the variance of the data is just u transpose sigma u. And then this is just the formula of the median absolute deviation squared on that particular direction, and take minimum, you get what is called the covariance matrix steps. The maximizer of it is not a direct estimator of the covariance matrix. You have to scale it back by a constant beta that depends on a Gaussian quantile function, because there is a constant shift. There is a constant difference between median absolute deviation and the standard deviation. One is an estimator of the quantile, the other is an estimator of the second moment. Okay, but then for this particular estimator, it will achieve the minimax rate of the problem under Huber's epsilon contamination model with respect to the squared operator norm. Right? So here is a table that we can actually define or modify depth function to solve other statistical estimation problems. For example, you can do that for reduced rank regression, Gaussian graphic model, and even sparse PCA using depth function. And for all these problems with respect to different loss functions, you can achieve the exact minimax rates of the problem by using depth functions in different ways. So one common feature of these minimax rates you can observe is that it always consists of two terms. The first term will always be the minimax rate when epsilon is 0, when there's no contamination. And the second term is always proportional epsilon squared, which depends on something called modulus continuity that models the difference between total variation and the loss function you use. Right? And these are all the minimax rates of the problem that you cannot improve. Okay, so we can see that the depth function is a very useful idea. But the practical question is, how do we optimize it, right? People have spent years and years trying to just compute Tukey's median, and they cannot. And people usually believe this is an NP hard task that you cannot compute. And personally, we also try to compute it by ourselves by writing down the code and to see how good or how bad it is. We managed to compute the Tukey's median when the dimension is very low. The largest dimension we can incorporate is when p equals 10, right? So when p equals 11, we just failed. We cannot even get an answer. Maybe we'll wait for another year, we will get the answer, but this is very slow. This is not like when you compute L0 penalized regression. It's combinatorial, but in practice you can still do something. But for Tukey's median or other regression depth function, you cannot do anything. So maybe a more humble question is it possible that I can design some practically good algorithm that you can at least use in practice and have good numerical results? That's the goal I'm trying to talk about in the second part of my talk. Okay, so I also want to mention that for some specific problems, such as the Gaussian mean estimation, there are amazing developments in recent years. Now it is sort of well known that you can provably achieve the minimax rate with an extra polylogarithmic factor by using this idea of higher moment certification, which are proposed by these authors. But the reason we still want to advocate Tukey's median is because of its indispensable statistical properties, right? So I list a few. But the most important property, I think, is the third one, that the Tukey's median is not only optimal for multivariate Gaussian mean estimation, it is actually optimal for any elliptical distribution, right? So you can think of the situation where maybe you have a multivariate Cauchy distribution. The first moment does not even exist, so you cannot estimate the mean. But you still want to locate the center of the data. And then Tukey's median also give you an optimal estimate of the location of the center of the data, right? So Tukey's median is designed for estimating the population mean, while the literature, the robust mean estimation estimator in the literature are designed for estimating the population mean. When median and mean are different, then they are fundamentally different. Okay, so to talk about, before talking about how I can do that, let me first deviate a little bit, talk about the framework of F-learning. So here, let me first review the definition of F-divergence that measures the difference between two probability measures, P and Q, by this formula. And this is a general notion of divergence that includes a chi-squared Kullback-Leibler and total variations, etc., as special cases, right? So f is a convex function, and because of that, you can write f as the supreme of a bunch of linear functions, and this f star that serves as intercept here is called the convex conjugate of the convex function f. And if you plug in this representation, you will be able to obtain the following variational representation of the f divergence. And this is kind of useful. And the optimal testing function t is achieved when t takes this form, that is, when t equals the derivative of f evaluated at the likelihood ratio test between p and q. Okay? And since you know the optimal t has to take this form, you don't have to take sup over all t. You only need to take sup over a class that contains this function, and your variational representation will be sharp. And in particular, since I know the optimal t has to take this form, I can just take sup over all functions of this particular form by replacing p by another q tilde, and then take sup over q tilde. And when q tilde equals p, the supreme will be achieved. So this is a different version of the variational representation of the f divergence. We have two different variational representations. So for these two representations, if you replace the expected value by the sample average, then this is just the sample version of the f divergence that measures the difference between the empirical measure and a given probability q. Okay? So then you can just minimize q to define your estimator. And the first estimator defined in this way is called f-GAN. That is proposed by these people in Microsoft Research. And the second formula does not really have a name, so I just call it f-learning to distinguish from the definition of f-GAN. Okay? So the framework of this f-learning is very general. And in particular, if you take f to be the function that leads to Jensen-Shannon divergence, then you are able to recover the original GAN that is proposed by Goodfellow's group. This is where the deep learning people start to use GAN to learn generative distribution for images. And if you take fx equals x times log x, then you just recover the definition of maximum likelihood estimator, right? And if you take f that leads to Haninger square, this is related to what is known as the rho estimator that is extensively studied by the French statisticians Barrault and Lucien-Berger. And finally, what is related to us is if you do total variation, then you get the depth function. Okay, and I'm going to show you why. So let's take fx to be the positive part of x minus 1, and then its derivative is just the indicator function. Therefore, the total variation learning formula can be written in this formula. Okay. And for example, if you want to estimate the normal mean, what can you do? The only thing you need to do is to specify the two classes of distribution that you need to deal with. So let's specify the first class distribution script q by the normal location model. That's the natural choice. For the second class, we also take the normal location model, but the difference is that we take theta tilde to be only in the neighborhood of theta with radius r. I'm doing that because you only need to distinguish theta that are close from the truth. Okay? So once you have this choice, then I'm going to send the radius r to 0. What I can obtain from this process is exactly the definition of Tukey median. Okay? So this is kind of interesting because before that, we have a good intuition of Tukey median. We understand that it is a process of projecting data and then try to calculate univariate median and then combine them. But this process tells you that Tukey's median is nothing but the minimizer of a sample version of total variation distance. And this also explains why it is minimax optimal in this Huber's absolute contamination model, because Huber's model essentially misspecification with respect to total variation distance. And what Tukey's median does is exactly try to minimize total variation distance. That's why they are compatible with each other. Okay, so you can also do the same thing for the covariance matrix estimation. And for this task, the first class can be specified as the covariance matrix model. And the second class, I'm going to restrict sigma tilde only in the rank 1 neighborhood of sigma. So this is kind of important because you cannot let sigma tilde to be in the arbitrary neighborhood of sigma. That will be not even Fisher consistent. So there is a subtlety here. You have to specify this rank 1 neighborhood. And then I'm going to let R goes to 0. What I can obtain is the following formula. So this is very closely related to the matrix depth function that we proposed in 2015. And at that time, we do not understand that. So we just proposed the matrix depth function by following Tukey's intuition. But now it is sort of satisfying to know this is just GAN. Okay? And you can do the same thing for the regression model. And the regression depth function can be recovered in the same way. So the F-learning framework is actually interesting. It sort of gives you a link between the two areas of robust statistics and deep learning area. So at least by two directions. For the first direction, you can imagine we can actually borrow those good optimization procedures from the deep learning community to solve those robust estimation problems. And the other direction you can think of is we have many good theoretical developments in robust statistics community. Maybe that can help you to inspire some of the theoretical foundation development for deep learning problem. Okay. All right. So in the rest of my talk, I'm going to focus on the second direction, try to convince you why those algorithms in the deep learning community can be used to optimize things that is close to the depth function. So since I already said that Tukey median is the minimize of total variation distance, is regarded as a special case of total variation learning, we can start by looking at this total variation GAN. Okay? So the definition of total variation GAN is trying to distinguish the empirical distribution from a normal location model by a logistic regression classifier. The reason I'm using logistic regression classifier is because this is the simplest classifier I can think of. So you always start with something simple and to see if it works. So the good news is that it does work because both this formula and Tukey's median can be regarded as variation lower bound, can be regarded as trying to optimize variational lower bounds of total variation distance. And this is even a sharper variational lower bound compared to that of the Tukey's median. And that's why it works. Right? You can show that this estimator can also achieve the minimax rate of the problem. Well, the bad news is that you cannot really optimize it. Optimization is really hard. We try to compute it on by ourselves, but even if you start your algorithm by some good initialization in a good regime, it will still start to diverge once you doing this alternating gradient descent and gradient ascent algorithm. And later we try to plot the TV GAN landscape, and then we sort of understand why it will have this very strange behavior. So in one word, it does not work. So the next thing we can look at is Jensen-Shannon GAN, because this is the original GAN that people have some success in learning complicated distributions of image. Here, my goal is just to learn this normal location model, and how hard is that, right? So. But you still need to, besides writing down this definition, you still need to specify what kind of classifier you need to choose. So here, before I tell you the right classifier to choose, first let me show you some numerical experiments. So the numerical experiments, we generate IID sample from the mixture model. So this is a Gaussian location model, and it's contaminated by another location model. The contaminating vector is theta tilde to distinguish from theta that we are trying to estimate. Okay, so we try different classifiers. They are basically neural networks with different structures. And in the first case, the neural network has only one layer, so it is equivalent to the logistic regression in the previous slides. And these structures have some hidden layers, and they sort of have different behaviors. And in terms of optimization, there's no problem. you can code it, and if you run it on GPU, usually it's very fast. Okay, so for the first classifier, what we observe is that you will always get an optimizer that is very close to the overall mean, which is the average of the true mean and the contamination mean, right? So this means that the estimator basically has the same property as sample average. That means it is not robust. Well, but once you start to have hidden layers in your neural networks, then things get robust, it works. And why? So we are trying to understand this phenomenon. So the lesson we learned from our numerical experiments is that a classifier with hidden layers leads to robustness, and we are trying to understand the reason. Jason?
Yeah, how does the constraint on script T translate to constraints on neural net parameters?
Could you rephrase your question?
In the max, there's a constraint. There's a function class. It's max over script T. How does that translate to a constraint on neural net parameters?
So for this one, the formula is just given by the same logistic regression here, right? So that's the one-layer neural network. If you have a two-layer neural network, you are going to replace this x by another sigmoid. That's what I mean by a multi-layer neural network.
So I think the class T there is given by a network architecture. Right?
Yeah.
No constraint on the coefficient.
There's no constraints on the coefficient.
Oh, there is constraint on coefficient.
That's my question.
Yeah.
What is the constraint?
There are L1 and L2 constraint on coefficients. Mostly I'm using L1.
I see.
But here I didn't give the detail. Okay. Yeah, okay, so we are trying to understand why this phenomenon happens, and then we got an answer. So let me define this, what I call the Jensen-Shannon divergence, a local version with respect to G, right? So this is a divergence function between P and Q that is distinguished by a logistic regression using the feature G. So G is a multivariate function that maps a multivariate data from the p-dimensional space to a d-dimensional feature space. And then it defines a divergence function. The proposition we have is that this divergence function is 0 if and only if the expected value of G is the same under both distributions. So this means that if the features are the same under both distributions, then the divergence is not able to tell apart the distributions. So that implies if you are trying to minimize the Jensen-Shannon GAN, you are more or less trying to match the moments that you have in your classifier. And in the previous experiments, if we use a single layer neural network, logistic regression, this is saying that Gx equals x. So what you are trying to match is just the moment of x, the first moment of the data. And of course, you will get the empirical average because that's the empirical first moment, and that's not robust. But when you start to have hidden layers in your neural network, what you are actually matching is the nonlinear moments. That's why it leads to robustness. So nonlinearity in the neural network is in the classifier is actually very important, and we can indeed prove that. So for a neural network with at least one hidden layer and a proper regularization, as you just asked, we have the following rates of convergence. If you use those bounded activation functions, things will get a bit easier because it is bounded. If you want to use ReLU, you can only use that after the top two layers because it's not bounded. But anyway, the rates are almost optimal, except here we have log P here. Okay, so that's for mean estimation using neural nets. What about unknown covariance? So the previous theorem assumes that covariance matrix is identity, right? So what if here we have an unknown covariance structure that we try to adapt to? Remember, Tukey's median does not have a problem. That's why we like Tukey's median. And here, what can we do? Well, there is a simple modification that you can just modify the generator class. Okay, try to make your generator class more general. So replace identity by gamma. And then not only do you maximize over the mean vector, also maximize over the covariance matrix. And then that will work. So you do not need to change the discriminator class. You will eventually get two estimators. theta hat will still be minimax optimal. For sigma hat, you just throw it away because it may not be accurate. So here's a general principle when you try to adapt to Newton's parameter when using this GAN type estimator, that basically you are free to modify the generator class. It will not affect the statistical complexity of the problem. The statistical complexity is only determined by the discriminator class. Okay? And you can think of the situation that we want to adapt to an elliptical distribution. What you can do is to modify the generator class to incorporate that. Thank you. And then not only you can maximize over these two parameters, you can also maximize over the marginal shape of an elliptical distribution, and that will also work. And I'm not going into detail. So the last topic I'm trying to cover is some ongoing work for estimating covariance matrix using this idea. Again, you can write down the GAN formula for estimating the covariance matrix by using this generator class. So here, for simplicity, let's assume that mean is 0. So I'm only going to specify the classifier, the class of discriminator to define the estimator. So I'm going to tell you two classes that do not work, and then I'm going to tell you some simple modification for the two classes that actually work. So here are the two classes that do not work. So the first class is a two-layer sigmoid neural network. This class do not work. It's kind of surprising because this class we prove it is optimal for mean estimation, but for covariance matrix estimation, this is not consistent, right? And the second class is a simple modification. You change the nonlinearity of the hidden layer to ReLU, and things were getting better because if there is no contamination, it actually works. It's optimal. But the problem is that it is not robust. Okay, so these are two counterexamples that do not work, but actually you can make simple modification to make it work. So for the first class, the only thing you need to do is to add an extra intercept neuron, right? So add a 1 here, and then it will work. When people model data by neural networks, adding intercept or not is really a matter of whether you standardize your data or not, right? It's not essential, but here it is sort of fundamental. It will determine whether things work or not. And if you want to use a ReLU activation function, what you can modify is to add an extra hidden layer in front of it, then it will work. So this 3-layer structure also works for covariance matrix estimation. And for above two neural network class, we can prove that resulting estimator achieves the minimax rate with respect to the squared operator norm. Okay, so here is some numerical performance. We try to record the time against the dimension. Remember, previously I told you that for Tukey's median, it only works for p equals 10, but now 5,000, no problem, and it seems to grow well, right? So we are satisfied with the practical performance. Okay, I think I'll stop here and take some questions.
Questions?
What is the intuition behind, so you change the architecture of your network, sometimes it works, sometimes it doesn't?
It's basically the proposition I showed that, that says that the minimizing GAN is more or less like matching the moments. So if you know what kind of moments you need to match in a robust way, then you can do reverse engineering to translate into the neural network structure.
Is it important to use neural network other than like other class of functions?
You don't have to use neural network as long as, but at least for the normal mean estimation setting, I think the 2-layer neural network is the most natural classifier because the proposition says that whatever feature you start to use from the second layer will be the moment you match, right? And Tukey's idea is that you need to match the first moment for each different direction. And if you add a sigmoid, that will give you nonlinearity. Put it on the second layer, that will give you the 2-layer neural network structure.
Jason?
I was in your generator. Why is it always the generator is only 2 mixtures of Gaussian? Your generator, it was always just mixture of 2 Gaussians. Why is that? I thought the contamination model was anything.
No, the contamination model it can be any distribution. So when I say I have a mixture of 2 Gaussian, this is just a numerical experiment. I just told you I have done this numerical experiment, and here's my observation. But later, when I prove theorem, that's for any contamination.
Oh, I see. So when you implement it, the generator is a mixture of 2 Gaussians.
Yeah.
But for the theorem, it's anything.
Yeah,
I'm sorry.
that's right.
But the discriminator is a neural net for the theorem.
That's right.
But the generator is everything. Okay.
In this top formula, you have the average over eta log 1 minus t of x. Can you compute this analytically for any t, or you sample and...
What people do in the deep learning literature is to, because you can sample from distribution, is to replace the expectation by a simple average. And then you can use gradient descent and gradient ascent to do that.
So this method, how tight is it to the assumption that the p theta is multivariate Gaussian? What if it's just a sub-Gaussian random variable?
That
You want to compute the mean of a sub-Gaussian random variable.
So you can generalize that by making the discriminator more general, right? So if you want to include all elliptical distribution, then try to optimize over all elliptical distributions here. If you want to incorporate all sub-Gaussian distribution, then you also need to do it here. So it cannot be adaptive to any distribution that are not specified in the generator class. That is very important.
You have to know p theta.
You do not have to know. If you do not know, then optimize over it. The message is that it does not affect the statistical complexity. The complexity is only affected by the class of the discriminator. So here, it's really an identifiability problem. As long as you make him, you can make it arbitrary general. As long as things are identifiable, it will be fine.
So if I understand, you show good quality results when your model is at the global optima.
That's right.
So how do you know that you're at the global optima, and how do you know how long it's going to take you to get to it?
Yeah. Okay. So I'm going to just throw the question to these people. I don't have an answer, honestly. It's just a matter of experience and the tuning.
Can you get any idea of what the least favorable distribution Q looks like?
Okay.
In ordinary robust statistics, for example, yes.
Okay. So I cannot tell you the exact least favorable Q look like, but for this class, we have experience, right? So if you do JS-GAN, the least favorable Q theta tilde is very close to theta. It's about epsilon away from theta, but not for total variation GAN. So for total variation GAN, it's actually the further the contamination, the harder it is, because if it's very far, the landscape becomes a problem. Then it will be stuck at local, which will cause a problem. So depending on the loss function, I think what you are really asking is in terms of information theoretically, but that I don't know.
Okay, if there is no other question, we thank Chao again.